Thank you very much, Chris. It's wonderful to be here. What a fantastic venue. It's the most wonderful venue. Thanks for coming tonight on a very rainy night. I'm going to talk to you about black holes. And before I start, I thought I would try and tell you something weird about black holes that might whet your appetite. And that is, if I was a black hole and I were to turn around like this, there'd be nothing any of you could do to stop yourself swirling around with me. It wouldn't matter if you had the most powerful rocket imaginable. If you had access to all the energy in the universe, you could not stop yourself whirling around with me. Space-time is glued to a black hole, and it kind of spins at the centre of an irresistible tornado of space-time. Now, a black hole is a region of space where gravity is so strong that nothing, not even light, can escape. And the term was only coined in 1967 by an American physicist called John Wheeler. And John Wheeler was the supervisor of another physicist who you may have heard of, Richard Feynman, who I was fortunate enough to be taught by when I was a student at Caltech. And before Wheeler coined this term black hole, there was pretty much no research on black holes. And immediately afterwards, the amount of research kind of mushroomed. And it just shows you the importance of getting the right word, the right phrase that paints a vivid picture in people's minds. And it's such a vivid picture, there's probably no one on the planet who doesn't know the term black hole. And we talk about it in everyday language. We say, you know, I've lost my passport down a black hole, I've lost my pen, that kind of stuff. But in many ways, this term black hole paints entirely the wrong image. Because far from being black, the black holes we see in the universe are among some of the most prodigiously luminous objects in the whole of the cosmos. And although we do see material just about falling into black holes, it's quite hard to see. The most striking characteristic of black holes is material coming out, often in fantastic titanic jets that stretch for millions of light years across space. So my book is about how black holes have come in from the cold. So just over about a century ago, black holes were so ridiculous as to not even be the preserve of science fiction. But gradually, over the last century, they've moved more and more into the centre of physics, the centre of astronomy, and we now suspect that they play some key but mysterious, still mysterious role in creating the universe of galaxies we see around us, and in fact in you sitting here listening to me today. So I'll explain that a bit later. So my story begins with this man, Karl Schwarzschild. He was director of the Berlin Observatory at the outbreak of the First World War in August 1914. And he immediately joined the German army. He didn't have to volunteer. He was 40 years old, but he was Jewish, although he wasn't practicing Jew, and anti-Semitism was on the rise in Germany, so he wanted to show that he could be a loyal German. And he ran a weather station in Belgium, he calculated shell trajectories in France, and he ended up in the end of 1915 at a place called Mulhouse, which was on the Alsace front. That was northern France, between France and Germany. And it was the only bit of the Western Front that was mountainous. And in November 1915, he went on leave. It was 800 kilometres by train to Berlin to see his family. And on the 18th of November 1915, he attended a lecture by this man. This is Albert Einstein in his rock and roll phase. Now, Einstein, in a series of 4 lectures, given one a week in November 1915, presented his revolutionary new theory of gravity, general relativity. Now, Newton had assumed that there was a force of gravity between the Earth and the Sun, like an invisible tether that kept the Earth trapped in orbit around the Sun. But Einstein realized that was incorrect. What a mass does is it warps the space-time around it. I can show you. So, of course, we can't see it because space-time is a four-dimensional thing and we are three-dimensional beings. And that's why it took the genius of Einstein to be able to recognize that. But what the Earth actually does is it travels kind of around the upper reaches of this valley in space-time, just like a roulette ball in a roulette wheel. So Einstein realized that gravity is actually the invisible curvature of space-time. That's all it is. Now, Schwarzschild was completely captivated by this theory, and he went back to the Western Front, and in between calculating shell trajectories, he worked on this theory of Einstein's. And the key thing you needed to do was to work out the gravity for any particular distribution of mass. So in other words, you needed to know the curvature of space-time for any mass. But the problem was, Newton had one formula to describe gravity, but Einstein had 10. So to find the curvature of space for any given mass was incredibly difficult. But within a couple of weeks, Schwarzschild did it. He found a formula for the valley of space-time around a spherical mass. And he wrote to Einstein in Berlin, and Einstein was amazed to get a letter from the Western Front. And he was also amazed to see that this person had done something which he thought was impossible, find a solution to his equations of gravity for a spherical mass. And he later presented Schwarzschild's work at the Prussian Academy of Science, but Schwarzschild hadn't finished. He realized that if the mass became more and more concentrated, gravity or the curvature of space would become more and more extreme. And eventually, the valley of space-time would become a bottomless pit from which nothing, not even light, could escape. And of course, we know that as a black hole, it would be shut off from the rest of the universe. Sadly, the same time, December 1915, Schwarzschild got blisters in his mouth, and they spread all over his body, and they were bleeding, weeping blisters, and it took a while for him to be diagnosed with a condition called pemphigus vulgaris, which is a condition where the immune system attacks the skin. Now, of course, your skin is your barrier against microorganisms, against pathogens, disease-causing organisms. So if that is breached, you're going to die. And unfortunately, Schwarzschild was sent back to Berlin, and he died in May 1915. Even today, there is no cure for pemphigus vulgaris. It can be controlled with steroids. But though he died, the idea of black holes did not die. Now, Einstein did not believe in black holes, and the reason for that was if a black hole formed, it was formed when a star died. So a star burns some kind of fuel, and in this 1915, 1916, nobody knew what that fuel was. But it was obvious that eventually that fuel, which generates the heat to push back and stop gravity crushing a star, eventually that fuel would run out, and the star would start collapsing down. And as it got denser, the gravity would get stronger, and eventually it would become a black hole. And that collapse would keep going until you had an infinite density point at the center, what we call a singularity. And this is when everything explodes. Density explodes to infinity, skyrockets to infinity. And when you get a singularity in a mathematical formula, it's telling you that there's something wrong with your theory. You've stretched your theory beyond the point where it has anything sensible to say. So that's why Einstein did not believe in black holes, because he spent 10 years developing his theory of gravity, and within a couple of weeks, someone from the Western Front had written to him to tell him that there was a flaw in his theory, so he didn't believe in it. And anyone who thought about this didn't believe in it either, because it just seemed ridiculous that you would get this singularity. So everyone who thought about it thought there had to be some other force that would intervene and stop a star at the end of its life shrinking down to form a monstrous singularity. And in the 1920s, it looked as if there was such a force. It came from quantum theory. Quantum theory is our description of the submicroscopic world of atoms and their constituents. And this is Wolfgang Pauli. Wolfgang Pauli was an Austrian physicist, one of the founders of quantum theory. When he was 20 years old, he attended a lecture of Einstein's, and at the end of the lecture, he stood up and turned to the audience and he said, "What Professor Einstein has just said isn't completely bonkers." So he was slightly arrogant. I think he was slightly arrogant. But he's famous for what we call the Pauli exclusion principle. And this is a quantum principle that essentially says electrons cannot sit on top of each other. Okay, and that's the Pauli exclusion principle is the reason that matter has extent, that matter doesn't collapse down to nothing. It's the reason this table is solid, the floor is solid. It's the reason we have objects. And so if you imagine a star collapsing at the end of its life because it's got no heat to push outwards, eventually the electrons would be forced really close together. But they have this great aversion to being put on top of each other. And this would cause them to fly about faster and faster to try and get away from each other. And this motion would create an outward force, rather like water drops, rain on a tin roof, you know, this constant push of these electrons. And so it was realized that the collapse would stop when you got an object called we call it a white dwarf now, where about the size of the Earth, but the mass of the sun. So whereas in a normal star, it's the heat being generated that pushes outwards and stops the star collapsing. In a white dwarf, it's this pressure of electrons which comes from the Pauli exclusion principle. But there was a spanner in the works. In 1930, this man, Subramanian Chandrasekhar, was coming from Bombay to England on a ship, and he was 19 years old. And as the ship went through the Suez Canal, he sat on deck in a deck chair with his textbooks, and he thought about dying stars. And he thought about white dwarfs, and he realized that everyone had forgotten something important. Yes, quantum theory was important to provide this pressure from the electrons, but so was Einstein's theory of relativity, his 1905 special theory of relativity, which effectively says nothing can travel faster than light. So these electrons, as you push them closer and closer, they buzz around like angry bees, but there's a limit to how fast they can buzz around because they can't buzz around faster than the speed of light. And so what Chandrasekhar realized, that if the mass of the star were big enough, if gravity was strong enough, this outward pressure from the electrons would be overcome, and the collapse would continue down to a singularity. So it looked as if black holes were unavoidable. This limit is about 1.5 times the mass of the sun. It's called the Chandrasekhar limit. This picture changed. Sorry, that's Einstein in his bodybuilding face. So I should have shown you that before. That was to illustrate speed of light being the limit. In 1932, the neutron was discovered at Cambridge, and this changed things a bit, because if a star was bigger than the Chandrasekhar limit and it kept collapsing, so electron pressure was not enough to halt the collapse, eventually the electrons would be driven into the protons to make neutrons. And neutrons obey the Pauli exclusion principle as well. So if you push them close together, they start flying around. And they provide an outward force. And so there's another stable state called a neutron star. And this is an object about the size of Mount Everest, but the mass of the sun. So a single sugar cube of neutron star material would weigh about as much as the human race, so a super dense object. The limit here, if the object was more than... The problem is the force between neutrons is more complicated than between electrons, so we're not exactly sure of the limit. But a neutron star would form, but if the star was more than maybe 2.5 to 3 times the mass of the sun, even this neutron pressure could not stop the collapse, and it would continue down to form a black hole. So black holes are unavoidable. And in the 1930s, this man imagined gravitational collapse to form a black hole. His name's Robert Oppenheimer, and he was the father of the atomic bomb. And he imagined gravitational collapse, a cloud of dust. In physics, dust is just stuff that doesn't interact. And he realized, he imagined what would happen as the object collapsed. It would shrink and shrink and shrink. Gravity would get stronger, the space-time would be more and more warped until you got to a point where light could not escape. And this is what we call the event horizon that surrounds the black hole. It's an imaginary surface, the point of no return for infalling light and matter. And the star would continue shrinking down to form a singularity. But he also realized that from outside, this would look entirely different, because one of the predictions of Einstein's general theory of relativity was that time flows more slowly in strong gravity. So if you were looking at this collapse from outside, you would see as the gravity got stronger, as space-time became more curved, the collapse would appear to slow. And the star would never, ever get to the event horizon. So there was this real great disparity between the time of someone who collapsed with the object and someone who was observing it from outside. So when the black hole formed, if you were to hover on just outside the event horizon, time would flow so slowly for you compared to the rest of the universe that you could watch the entire future history of the universe flash past your eyes like a movie in fast forward. So Oppenheimer imagined this collapse. He worked out how it would happen, but he made one gigantic mistake. He thought that black holes would not be visible because he thought they were black and they're small. How are you going to see a black, small object against the black of space? If he talked to any astronomers, they would have told him that it was very unlikely that a star would actually be on its own. I mean, our sun is very unusual in being a solitary star. Most stars are in groups, they're binaries, or there may be 3 or 4 stars. And this, having a companion, makes all the difference. I'll show you why. So fast forward to 1971, and this is Hurstmonceux Castle in East Sussex, which is near Hastings. And it was the site of the Royal Greenwich Observatory. It was a 16th century castle surrounded by a moat. And in 1970, this man, who was 30 years old, his name's Paul Murdin, he came back from America where he'd done a PhD at the University of Rochester in New York, and he'd done a postdoc, and he came back and he had a short-term post. But he was desperate to get a full-time job because he had a wife and 2 young boys, and he really needed a job. So he desperately needed to make his name. He needed to make a discovery. But the problem in astronomy, is that there are 2 trillion galaxies, and each has got about 100 billion stars. So there are more stars in the universe than there are sand grains around the margins of all the continents on Earth. How do you find an interesting sand grain? How do you find an interesting star? That's the problem. And when Murdin was back in New York, him and the other graduate students used to sit around drinking coffee thinking, how would you find an interesting star? And Murdin realized that if it emitted X-rays, it would be interesting, because X-rays are emitted by matter at millions of degrees. That's bound to be interesting. Well, in the early 1960s, X-ray telescopes were launched on sounding rockets. These are rockets that just went up in the air, above the atmosphere, and then came back down again. Fortunately for us, the atmosphere absorbs X-rays. But in the minute or so they were above the atmosphere, they could look at the X-ray universe. And they discovered lots of X-ray sources. But these X-ray telescopes were incredibly crude, and it was very difficult to locate where these X-ray sources were. So they were just given, they were named after the constellations. So one of them was called Cygnus X1. But in 1970, just as Paul Murdin was coming back to England, to the Royal Greenwich Observatory, this was launched. This was by NASA. This is Uhuru, which was the first X-ray satellite. And above the obscuring atmosphere, it was able to find hundreds of X-ray sources. And Murdin got hold of a catalogue from this satellite, and he realised that the box showing the location of this object, Cygnus X1, had shrunk. And he looked and he saw that there was one interesting object in that box, and it was a blue supergiant star. So this is a star that's maybe 30 or 40 times the mass of the sun, pumping out maybe 100,000 times the light of the sun, a really extraordinary star. But he knew that couldn't be the source of the X-rays, because even a blue supergiant star has a surface temperature of only about 30,000 or 40,000 degrees. That's not hot enough to produce X-rays. But Murdin thought, did it have a companion? Because if it had a companion, then material could be sucked off the blue supergiant and it could swirl down onto the companion star, rather like water going down a plug hole, and friction, as it swirled down, could heat it to millions of degrees. So did it have a companion? That was the key thing. His luck was to be sharing an office. It was an octagonal turret room with this woman, Louise Webster, who's been entirely written out of the history of science. But she was Australian. She was 1 year older. She was 31. She'd worked in America as well. And she was working with Richard Woolley, who was the director of the Royal Greenwich Observatory, on measuring the speeds of stars. Well, if, as Murdin suspected, the blue supergiant star was orbiting something else, then periodically, as it went round the invisible object, it will be coming towards us and then going away from us. Now, we all know if a police car comes towards us, the pitch or frequency of its sirens increased. And if it goes away from us, the pitch is lowered. And exactly the same thing happens with light. So if something's coming towards us, we see higher pitch light. The light is shifted to the blue end of the spectrum, which is higher frequencies. And if it's going away, it's shifted to the red. So was this effect happening? Well, Louise Webster went away to use the 100-inch telescope which they had at Hurst-Monceau. It was a 2.5-meter telescope. It was one of the biggest telescopes in the world. And unbelievably stupidly, it had been built in East Sussex, which was just about the worst place in the world to do astronomy because it was always cloudy and raining. And eventually, they dismantled it, and at a greater cost than it cost to build it, moved it to the Canary Islands. Anyway, she found immediately that the blue supergiant star was orbiting something that they couldn't see on their photographic plates every 5.6 days. And Murdin and Webster sat down at their desk in their octagonal office, and they used Newton's law of gravity to work out what was the mass of this invisible object. It was whirling this massive star around every 5.6 days. And they came to the conclusion that it had to have a mass of at least 4 times the mass of the sun, maybe more than 6 times. Today we know it's 15 times the mass of the sun. Well, remember the limit on a neutron star is only 2.5 to 3 times the mass of the sun. The only object it could be orbiting was a black hole. And they published in the journal Nature. And as I say, poor old Louise Webster has been written out in History of Science because she is the co-discoverer of black holes. And it turned out that Murdin got his permanent job. He got a house. He was the first person in history to have a mortgage paid by a black hole. And he celebrated with his 2 little boys and his wife. He bought them Knickerbocker glories in a Hastings beachfront cafe. This was in February. And I'm sure his sons, who were like 3 and 5, thought, I hope Daddy finds another black hole. And I just think, what an amazing contrast. The person who co-discovers black holes he celebrates with Knickerbocker glories, and the person who predicted them died of a horrible skin disease. That's an amazing contrast. But all they'd found was that there was an invisible object. They hadn't actually seen the object. The definitive evidence of the existence of black holes did not come until the 14th of September 2015. This is a 4-kilometre ruler made of laser light at Livingston in Louisiana, and 3,000 kilometres away in Hanford, Washington State, is another 4-kilometre ruler made of laser light. And on the 14th of September 2015, a shudder went through the Hanford ruler, and less than 100th of a second later, an identical shudder went through the Livingston ruler. And here you can see the traces of that event. So if you take the top panel, which I believe is, where is it? It's Hanford. The up and down motion you're seeing is the stretching and squeezing of this 4-kilometre ruler, by a fantastically small amount. And the middle panel shows you the stretching and squeezing of the Livingston ruler. And on the bottom panel, you can see them overlaid, and they're identical. And this is the unmistakable signature of the merger of two black holes. The gravitational wave signature. So gravitational waves were predicted by Einstein in 1916. So remember, he said that mass can warp space-time. It can also wiggle space-time. So that's what a gravitational wave is. And the event, this merger of two black holes, they were very large, many tens of solar masses each, happened more than 1 billion years ago. So at a time when the most complex organism on Earth was a bacterium, two monster black holes were kind of locked in a death spiral. They went around each other one last time. They kissed and coalesced, and they launched a tsunami of kind of tortured space-time, which spread out at the speed of light. And it spread out for 1 billion years, filling a greater and greater volume of space and therefore becoming more and more diluted until we picked it up in 14th of September 2015. And I just want to give you some, so this is the definitive evidence that black holes exist because the signature was unmistakable. I just want to give you some idea of the energy involved in this event. So when a hydrogen bomb explodes, and let's hope we don't see hydrogen bombs explode ever again, but when one explodes, something about 1 kilogram of mass energy is turned into other forms of energy, eventually the heat of the fireball, 1 kilogram. But in the merger of these two black holes, 3 times the mass of the sun vanished in a split second and instantly reappeared as gravitational waves. So briefly, the power in these gravitational waves was 50 times greater than the power given out by all the stars in the universe combined. So to put it another way, had this event not generated gravitational waves, but light, visible light, it would have shone 50 times brighter than the entire universe. So it was the most violent, the most energetic event ever witnessed by human beings. Now, it turns out that we're talking here about stellar mass black holes, but black holes were actually discovered about 8 years before Merdin and Webster discovered black holes. I'll explain. But no one knew it. No one realized at the time. They were kind of discovered by this man. He's Martin Schmidt. He was a Dutch American astronomer. In fact, he only died, I think, last year at Caltech in California. And the story starts, really, with radar in the Second World War. So radar was a technique of broadcasting radio waves which bounced off of aeroplanes. You pick up the echo and you can locate the aeroplanes. And we know that, we all know that radar played a major role in the defeat of the Luftwaffe in the Battle of Britain. Well, after the Second World War, some of the radar engineers decided to become astronomers. This was a really high-risk route to take because there was no expectation whatsoever that stars would be producing any radio waves. Most stars, like the sun, they emit what we call thermal radiation or blackbody radiation. It it's like a hump. You get a peak for the sun, it's green light, and then it tails off dramatically fast at longer wavelengths. Well, radio waves have 1 million times the wavelength of optical light, so there should be virtually no radio waves given out by stars. But to everyone's amazement, there did appear to be sources of radio waves in the sky. The problem that everyone faced was that because radio waves are 1 million times bigger than optical waves, the vision of radio telescopes is 1 million times blurrier. Okay, so if you have a given telescope, it's going to get, if it's the same size as an optical telescope, it produces an image which is 1 million times blurrier. So actually locating the radio sources and matching them with galaxies or stars was pretty impossible. However, in 1962, it turned out that one of these radio sources, called 3C273, it was discovered in Cambridge, in the third Cambridge catalogue, 3C273, was going to be occulted by the moon. So the moon was going to pass over it several times. Now, there's one thing we know about the moon. We know its location incredibly well. So if it was possible to observe when 3C273 vanished and when it reappeared, it would be possible to know its exact location. And then you could look at photographic plates and try and see if there's an object associated with it. And this observation was done by the Parkes Radio Telescope in New South Wales, which was actually designed by Barnes Wallis, who also created the bouncing bombs during the Second World War. It's in New South Wales. Okay, well, this is what they found. They located a position, they looked on the photographic plates, and there was a star where this object was. And it was a weird star because it actually had a jet coming out of it. So it was an unusual star. So the astronomers in Australia, John Bolton, who was English, but he'd built Parkes, the telescope I just saw, but he'd also had a connection with Caltech where he'd set up their radio telescopes in the 1950s. He sent to Martin Schmidt, he wrote him a letter and said, we found a location and there's this object here. Could you get its spectrum? So what astronomers do is they spread the light out from an object, and it turns out that nature has been very, very kind to us because particular elements like calcium and carbon and all these sort of things, they all have a particular fingerprint, certain colours that correspond to these elements. So we can identify in an object what it's made of, and that can tell us what it is. And so Martin Schmidt, just after Christmas 1962, went to Mount Palomar, which at the time was the biggest telescope in the world, 5-metre optical telescope, just north of San Diego, to take the spectrum of 3C273. And he failed initially, and the reason he failed was because he was used to using this telescope to look at the most distant and faintest objects in the universe. And you had to actually observe them for hours on end to soak up enough light to get a spectrum. But this object, 3C273, he didn't realise it was really bright. And so it completely fogged his photographic plate, and he had to do it again. And eventually, this isn't the spectrum, by the way, but this just shows you the lines, the black lines will correspond to different elements. And he took a spectrum of 3C273, but it made no sense at all. There was no spectral lines that corresponded to any known elements. And he went back to Caltech and he showed it to all of his colleagues, and nobody had any idea what they were looking at. And Bolton wrote to him from Australia and said, we in Australia are going to send a paper to the journal Nature about finding the location of 3C273. Can you provide an accompanying paper telling people about this object? And poor old Schmidt kind of was in a panic because there was literally nothing he could say about this object other than it didn't make any sense, which didn't make a very long paper. So in March 1963, he got this letter, and he came back from lunch, and he sat at his desk looking at this spectrum, and he could see there was some kind of pattern. The dark lines got slightly fainter as you went to longer red wavelengths, and he got slightly closer together. And he thought, well, I'll compare it with a known spectrum. And he compared it with one of the most familiar spectrum to astronomers, which is called the Balmer spectrum. This is from hydrogen. Hydrogen is the most common element in the universe, accounts for 90% of the atoms in the universe. And in a hydrogen atom, the single electron can drop from one energy level to a lower energy level when it gives out light. And the Balmer lines are created when an electron drops to the second energy level. So when it drops from the third to the second, fourth to the second, fifth to the second, you get the Balmer lines. So he began comparing these lines with the Balmer lines, and he immediately saw that what he was seeing were Balmer lines in this 3C273, but shifted by 16%. Now, this meant that whatever the object was moving away at 16% of the speed of light. Now, no one had even ever observed the star that was even moving at 1% of the speed of light. So this was really mystifying. But in the late 1929, Edwin Hubble, the American astronomer, had discovered that the universe was expanding. Its galaxies, its constituent galaxies, like our Milky Way, were flying apart from each other like pieces of cosmic shrapnel. And if you ran that expansion backwards in your mind, you came to a point about 14 billion years ago, which we now call the Big Bang. You know, that they were rushing apart in the aftermath of an explosion, the Big Bang. And the further away a galaxy was, the faster it was moving. But 3C273 was moving so fast, it had to be 1,000 times further away than Andromeda, which is our nearest galaxy. And yet, it was a star which was really, really bright. And when Schmidt did the calculations, he realized that this star was pumping out 100 times the light of a normal galaxy. And it only appeared to be a tiny star. We now know that it was a galaxy, but it was so bright that we couldn't see the actual stars around the center. And within about a year, people had realized there was only one possible source of this light. I should tell you that also 3C273 fluctuated in brightness on timescales of days or weeks. That tells an astronomer that it has to be smaller than a few light days or light weeks across. So this object was probably the size of the solar system, but it was pumping out 100 times the light of an entire galaxy. And within a couple of years, a couple of astronomers realized that there was only one possible source. It was matter swirling down onto a black hole and being superheated to millions of degrees as it happened. But not a black hole of a few times the mass of the sun, a black hole of billions or even tens of billions of times the mass of the sun, a supermassive black hole. So we quickly realized that there were a lot of other galaxies. By the way, this 3C273 is known as a quasar, quasi-stellar object, a quasar. And quasars are part of a zoo of objects which we call active galaxies. In active galaxies, most of the light is not coming from starlight. It's coming from matter swirling down on a black hole. These are what active galaxies are. But it turned out that only about 1% of galaxies are active. So black holes probably were of no consequence in the universe. If they only account for 1% of galaxies, they're probably not very important. But everything changed with this. This is the Hubble Space Telescope. If you remember, in 1990, it was launched with the telescopic equivalent of a squint, and it cost $800 million to fix it. It was the most complex space mission by astronauts ever. They effectively put correcting spectacles on the instruments to correct it. And now the problem with observing the universe from the ground is rather like lying on the bottom of a swimming pool, looking up at the lights on the ceiling above the pool. You can imagine turbulence in the water causes the lights to move around and they get blurred out. And that's exactly what happens when we look at the stars and galaxies through the Earth's turbulent atmosphere. But Hubble was above that. So it had super sharp eyesight. And with that super sharp eyesight, it could see into the heart of scores of nearby galaxies. And in every single one, in the centre, the stars were orbiting far too fast. So fast that they should have been flung off into intergalactic space. And the only way that could not happen is if there was a very, very compact, very massive object in the centre of every galaxy. So we realised, Hubble discovered that in fact there's a supermassive black hole in the heart of pretty much every single galaxy. And the reason that only 1% are active is because only 1% are being fed. In the 99% of cases, all the gas and ripped apart stars has been eaten in the vicinity of the black hole, so it's slumbering. So that's why. So there's a supermassive black hole in the heart of every galaxy. But even then you think, well, they can't be that important, because although they're massive, they are unbelievably tiny. And their gravitational reach, even one of a billion solar masses, is only a few tens of light years, whereas the centres of galaxies are maybe 20, 30,000 light years across. So their reach is very, very tiny. And they are very small. So if you imagine a bacterium compared to a city, that's what a supermassive black hole is compared to its galaxy. It's like a bacterium compared to a city. It's that tiny. Now, could a bacterium control the street plan of London? Well, that would be completely ridiculous, wouldn't it? But it turns out that the supermassive black holes control the stars in their galaxies, which is, when it was discovered about 20 years ago, was thought to be so unexpected, it couldn't possibly be true. But in every single galaxy, we see that the supermassive, at the centre of the galaxy, there's what we call a bulge of stars, a kind of a spherical B-swarm of stars. And in every one of these galaxies, the supermassive black hole is 1/200th the mass of the stars. So there's some kind of intimate link between the stars and the supermassive black hole. They can't possibly be now because they can't. But it turns out that as far as supermassive black holes are concerned, size does not matter. Energy is the important thing. So if I walk past a house and a slate falls on my head, then what's actually happened is gravitational potential energy, that's the energy that the slate had by virtue of its high location in the gravitational field, as it's fallen to a lower place in the gravitational field, that energy has been converted into other forms. Energy of motion of the slate, energy of my headache. Now, if you imagine the formation of a supermassive black hole, and we don't know how they form, there's so many mysteries about these objects, we don't know how they form, but in effect, countless quadrillions of slates would come together to make such an object. And that would liberate a tremendous amount of energy. And in fact, a simple calculation shows you that the energy liberated in the formation of a supermassive black hole is about 1,000 times greater than the energy needed to blast a galaxy apart. So in other words, blast all of its stars to infinity. So you only need to convert a tiny portion of that into, only a tiny portion of that needs to be liberated to heat and disturb the gas around the black hole, the gas which is the raw material of stars, and there's a mechanism there where the supermassive black hole can affect the stars. And we can see this today because we see the accretion disks are millions of degrees, and they have winds of material, fast winds of material coming out, exactly like the solar wind that comes out from the sun. And in many of these objects, there are these twin jets which come out of the poles of the black holes. These accelerate many times the mass of the sun to almost the speed of light. I mean, we can do a Large Hadron Collider, we can do like a nanogram or something, you know, but these can do many times the speed, the mass of the sun to the speed of light, and these jets can extend for millions of light years. And it's by means of these jets that these tiny black holes can project their power. So this is an object called Cygnus A. I should tell you, in the 1950s, where it was discovered that the radio emission from these active galaxies came from two lobes, one on either side of the galaxy. So you can see a galaxy in the center and these giant lobes. And so it was obvious that there had to be a connection, but that connection was not found until 1983. This is an image taken by the Very Large Array in Socorro, New Mexico, 27 dishes in the desert. And you can see the jet going to the right-hand side. The jet is probably coming towards us, so it's being boosted by the Doppler effect, so we see it. The counter jet is going into the slide and is being reduced, so we can't actually see it. So what you're seeing is if you imagine a hose of water hitting a brick wall and that water splashing back, that's exactly what you're seeing. So the jet is hitting the intergalactic medium like a brick wall, and the material is just splurging backwards, and that's what you're seeing. So it's by means of these jets that these tiny black holes can project their power, and they can actually control galaxies. Now, if I said that there's a supermassive black hole in every galaxy, that must mean there's a supermassive black hole in our galaxy, and there is. It's called Sagittarius A star, and it was discovered exactly 50 years ago this year. These two started studying it around about year 2000. On the left is Andrea Ghez. She's an American astronomer in California. On the right is Reinhard Genzel, who's a German astronomer in, I think, Bonn. And they realized that this object, Sagittarius A star, which is 27,000 light years away in the center of the galaxy, had a cluster of stars around it. And if they could observe how these stars were moving, they might be able to determine how massive the black hole in the center of our galaxy was. Now, of course, they had the problem of looking through the Earth's atmosphere, which blurred all these stars out. So they've used a range of techniques. But one of the techniques they've used is called adaptive optics. So you have a telescope mirror, very thin, has lots of pistons behind it, which can move the mirror and flex it hundreds of times a second. And you fire a laser beam up through the atmosphere, and some of it gets reflected. And from the reflection, a computer can actually calculate how to flex the mirror to compensate for the turbulence in the atmosphere. So effectively, you get a telescope that's in space, even though it isn't in space. And with this, they were able to see, over decades, they were able to follow the motion of these S stars, about 50 of them. They're called S stars because it's Sagittarius. And they basically loop around the black hole. They move very fast, several times, 1 or 2% the speed of light, something like that, and they come back out again. And using Newton's law of gravity, they were able to determine from these orbits what the mass of the supermassive black hole is, and it's 4.2 million times the mass of the sun. And they won the Nobel Prize. I think it was about 2 years ago for that. And here's a huge mystery. Why is the supermassive black hole in our galaxy so tiny? In all, in the quasars, we're talking about tens of billions of times the mass of the sun, 10 billion, up to the biggest one, 60 billion times the mass of the sun. This is thousands of times bigger than our one. And if you compare us with Andromeda, Andromeda is the nearest big galaxy. Andromeda is a very similar spiral galaxy to us, yet its supermassive black hole is 50 times bigger than ours. So this is a complete mystery why we've got this little tiddler in our galaxy. But it's connected to you coming here tonight, because in the big galaxies with the big supermassive black holes with these jets, the jets push away all of the star-forming gas, and so they can snuff out star formation. So in these galaxies with the big supermassive black holes, they have one generation of stars, and then there's no more star formation. But in our galaxy, with a tiddler that can't do this, there have been multiple generations of stars. So the sun is a third-generation star. And in each successive generation, more heavy elements have been forged. So each generation forms from the kind of ash, the debris of the previous generation. So I'm talking about heavy elements like calcium and carbon and oxygen, all the elements that are needed to build a rocky planet like the Earth, all the elements that are needed to make you and me. So the reason you're here today is because for some unaccountable reason, we have an unusually small supermassive black hole in the centre of our galaxy. Now, what we've actually, when I talked about Webster and Murdin getting indirect evidence of the existence of a black hole by the motion of that blue supergiant star, and again, Genzel and Gez really have only got indirect evidence. What we wanted to do was see a black hole. And this happened because of the Event Horizon Telescope. The Event Horizon Telescope was an array of radio dishes, similar radio dishes with similar radio receivers across the world. In fact, initially 8. And I should tell you that I told you that with radio waves, you get 1,000,000 times blurrier view of the universe, but you can compensate for that by having a bigger telescope. But when you get a telescope which is more than 100 meters across, it collapses under its own weight. This has actually happened to a telescope in America. And so astronomers get over this by linking together separate radio dishes and combining what they see to effectively give them a bigger dish. So this is the idea here. So these the signals, they will all look at the same object. In this case, they would look at, I'll tell you, there's 2 black holes they looked at. And they would record the radio signal on hard drives, which would then be flown to 2 supercomputers, one of which is in Haystack in Massachusetts, and the other one's in Bonn in Germany, where they would be combined to create the image. And I should tell you, these images, this is a terrible telescope. Imagine if you had an optical telescope, with a silvered mirror, and you blacked it all out except for 8 tiny dots. That'd be a terrible telescope. Well, that's exactly what they're doing with the radio telescope. But of course, it's all we can do. And we got these images. So the first one was 2019, is M87. M87 is a nearby galaxy with a 6.5 billion solar mass black hole in the middle. Huge black hole. And you can actually see what you're seeing in the center there, that void, the edge of the void, you'd think it's the event horizon. It is the event horizon. But because of the distorted space-time, light rays don't come to us in straight lines. They can even orbit the black hole. So what we're seeing is a distorted version of the event horizon. It's called the shadow. Fortunately for us, it's bigger than the event horizon, so we can see it. And the material on the bottom, on the left-hand panel, is brighter, we think, because it's coming towards us and being boosted by the Doppler effect, and at the top it's going away from us. And when material, this hot material you're seeing, this ring of material, when it crosses over that boundary into the black hole in the center, this matter is never seen in our universe again. It goes over like water over a waterfall. On the right, you can see Sagittarius A star, which is our supermassive black hole. Now, our supermassive black hole is 1,500 times smaller than the M87 one. But by a weird coincidence, it's actually about 1,500 times closer. So they look exactly the same size, even though the one on the right is 1,500 times bigger. And the first image we got in 2019. The Sagittarius A star one we got in 2022, 3 years later. I can tell you why it took 3 years to extra analysis to get there. It's because being 1,000 times smaller, all the material going around it is going around 1,000 times faster. So if you imagine M87, if you think it is equivalent to a very elderly Labrador sleeping on the lawn, it'd be very easy to get to photograph it. But Sagittarius A star is equivalent to a very lively puppy hopping around. That's much more difficult to get an image, and that's why Sagittarius A star took 3 more years. It took 3 more years to get that image. And I'll just finish by, this just shows you the size of the M87 black hole. It's bigger than the actual solar system. And as I say, when material collapses through the event horizon down to the singularity, we believe that space and time itself fragment. They come apart into something more fundamental. We've got no idea what that is because we would need what we call a quantum theory of gravity, and we don't have that. But we think that they actually break apart. So I just want to leave you with this thought, and that is, as human beings, we often beat ourselves up a lot, because we've created global warming and environmental damage and done terrible things to our planet. But sometimes I think we need to pat ourselves on the back because we came down from the trees onto an African plain, 2 or 3 million years ago. We've got a brain which is just 1.5 kilograms of jelly and water, but we've seen to the edge of space and time. Thank you.